This is the intro to section 10.1, area under a curve. This section kind of starts off what would probably be, well, fundamental theorem of calculus kind of fits in here. It's one of the biggest ideas that there is in this course. Up to this point, the biggest idea really has been that the derivative is the slope of a tangent line, and you can find instantaneous rates of change for various problems and use that to solve all kinds of stuff. What comes from here on is basically finding areas under curves. So instead of finding the slope of the curve or the rate of change, we're finding the area under it. So to start off as an intro example, I've got this function y equals 2x plus 5. So we should be able to draw half decent job of that. 2x plus 5, so 1, 2, 3, 4, 5, and slope of 2, so something like this. And we're saying what's the area from 1 to some number x under there. So we can draw ourselves the area. And in this case, because it's not a curve, it's actually a linear function, we can use area of potentially a triangle and a rectangle to actually find an expression for this. So we're going to write this as an expression. We'll call it a of x, because I've said from 1 to x, not from 1 to a number. So we're not going to be able to give an answer like 10 here. We'll give an answer that has x's in it. But so let's take a look at this as the area of a rectangle plus the area of a triangle. So we know that that's going to be length times width plus the 1/2 base times height, if we can figure out expressions for all of those. So the width of this little rectangle is just x minus 1. That's I can just see the distance between those. And if I look at what the height of it is, it's right here. Now what that is f of 1, and if you look, f of 1 is going to be just 2 times 1 plus 5, which is 7. This is 7 units high right here. So 7 times x minus 1 is the area of that rectangle. Now if I look at the area of this triangle, I've got 1/2. Now the base of it is again x minus 1 units wide. But this point up here, I don't have a number for. I can only call it, f of x. So I could call it, the height here is f of x minus 7. F of x minus 7 could go in there. To simplify that out a bit, 7 times x minus 1 is 7x minus 7. Here I have a half x minus 1. Let's sub in 2x plus 5 for our f of x. We've got 2x plus 5 minus 7. Take that a bit further. We've got 2x plus 5 minus 7 is 2x minus 2. If I multiply that by half, I get x minus 1. So basically I have x minus 1 times x minus 1 here. If I expand that, I'll have 7x minus 7 plus x squared minus 2x plus 1. And finally, pull together my like terms, and I get an expression that says that the area function from 1 to x is x squared plus 5x minus 6. Now that by itself doesn't really get anyone too excited, but if you take a look at what's the derivative of the area function, it might surprise you what it is. It's 2x plus 5, which, if you recall, was the function we were given in the first place. And so this leads us to kind of, again, one of the biggest ideas that there is in calculus, is that when you're doing the area under a curve, you can get to that by basically doing the antiderivative. And so just to draw that in kind of a simple generalized way, if you want a real solid proof of that, you'll want to see in your textbook page 451 for a detailed explanation, kind of like when we did derivatives by first principles. This is essentially areas by first principles. If you look at that, I'm not going to hold you responsible for that for a test, but basically in general, if you are looking at a function, and we're, this time it can be a curve, and I've got my curve y equals f of x here, and I want to do the area from some point to some other point here, a to b, and I'm looking for that area, I can say, well, a prime is f of x, so the area function, if I evaluate that from a to b, is just the antiderivative of the function I was given. So if I call it big f of x to stay consistent with the notation we had earlier, where this is the antiderivative. When we get into area notation or an integral notation later on, we'll say something like this. We'll say that integral from a to b of our function f of x dx is equal to, and we'll be able to just do f of b minus f of a. So that, in a way, is the fundamental theorem of calculus. As it says, you're doing area under a curve. You take the antiderivative and evaluate it from a to b. So the next example, the next video, will give us some concrete examples of this.